Okay, welcome back. We are in chapter 17, dealing with buffer solutions. So the problem states, calculate the pH of a buffer that is 0.12 molar in lactic acid and 0.11 molar in sodium lactate. The Ka for lactic acid is 1.4 times 10 to the negative fourth. Okay, so in this chapter we learned about something called the Henderson-Hasselbalch equation. So that is pH equals the pKa plus the log of the base over the acid. Okay. All right, so calculate the pH, pH of a buffer that is 0.12 molar in lactic acid, 0.11. So we're given each of these values, and the Ka is 1.4. Now, remember that pKa, remember we said for pH, P means negative log. So therefore, pKa, just take the negative log of the Ka. So I'll do that here in my calculator to save space. And we'll set our formula, pH equals pKa, which happens to be 3.85. Again, that's the negative log of 1.4 times 10 to the negative fourth. Plus the log of the base. Now, sodium lactate, we have the lactate anion. That's the conjugate base. So you have lactic acid. Lactate is the conjugate base of lactic acid. So the concentration of base is 0.11 molar. And the concentration of acid is 0.12 molar. So plugging everything into your calculator now, you can easily solve. So pH equals 3.81. So remember, it's good to have a buffer system where the pH of it equals the pKa. Okay, pH equals the pKa. So I'm going to show you guys one more way to do this. So we will erase this. And again, this is using this. So this is the other way, not using Henderson-Hasselbalch. Okay, this is not using Henderson-Hasselbalch. Because remember, there's more than one way to do a problem. If you have not heard of Henderson-Hasselbalch, here's a way to do it. We can use an ice table. So lactic acid, let's just say HA goes to H plus plus A minus. So this is the way using the ice table. We are given 0.12 molar of lactic acid, and we're given 0.11 molar of sodium lactate. So I am just substituting HA, meaning lactic acid, and A minus for the lactate. So we're going to get some product formation. And, whoops, we're now going to set the Ka equal to products over reactants, right? Okay, so in this problem we assume that x is small. We assume that it goes to 0. So, as you can see here, we simply take 0.11, divide by 0.12. Okay, and then we take 1.4 times 10 to the negative fourth, divide by that answer. you get x to equal 1.52 times 10 to the negative fourth. Making a little bit extra space here. Just take the negative log of that. To get 3.81. So you get the same number as the Henderson-Hasselbalch, but this is not using the Henderson-Hasselbalch formula. So if you forgot it, if you haven't learned it yet, you could use an ice table. Okay, moving on. Calculate the pH of a buffer formed by mixing 85 milliliters of 0.13 molar lactic acid with 95 milliliters of 0.15. Again, this should be molar of sodium lactate. So again, remember when it says sodium lactate, they're really just telling you that you have a conjugate base. Okay, so the only thing we care about is going to be the lactate anion. And you can assume that sodium lactate, the sodium will fully dissociate from the lactate because it's a strong electrolyte. So you'll get sodium lactate. So if they tell you that you have 0.15 molar of sodium lactate, you know that you will get that literally the same concentration in solution of the lactate. Okay, so now this problem is a little bit different. They're asking 85 mils of some molarity. Now the first thing I do when I see a volume and a molarity is I want to multiply them, right? Because you know that molarity equals moles of solute per liter of solution. So the first thing I want to do is just multiply by liters of solution so that I'm left with moles of solute. That's just my habit. You know, I just really feel like doing that in every case. Okay. So I'm going to try the pen here. Let's see if we can bring that back. See if this will work. Okay. So again, we have two different volumes and molarities. We can actually use the Henderson-Hasselbalch equation. But, so the Henderson-Hasselbalch, if you remember, is pH equals pKa plus the log of concentration of base over acid. Instead of using concentrations, though, we can actually use molar ratios. So this demonstrates a key point that you can use molar ratios in the Henderson-Hasselbalch equation, provided that the number of liters, so you can do mole per liter over mole per liter. If the liters are the same, then you can just simply use moles. So let's find the moles of each thing. So we'll find the moles of lactic acid The pen is kind of acting up, so we'll be using finger again. So the moles of the lactic acid, we start with 0.13 mole per liter times remember things have got to be in liters, so they need to cancel out. So we get 1.3 times 0.085. I'm sorry, I screwed this one up. It's 0.085. Okay, so 0.13 times 0.085. We get 0.01105 moles of the acid. So now we need the moles of the base, or lactate. So again, that will be 0.15 moles per liter times 0.095 liters. So we get 0.101425 moles of the base. So again, making a little bit more room here, we are simply going to plug into the Henderson-Hasselbalch using these two values. Okay, so just kind of a fun color. So pH, and again, pKa, right, is going to be the negative log of the Ka, so that's given above. 1.4 times 10 to the negative fourth plus the log of the base over the acid. So plugging into our calculator, we get the pH to be 3.96. So just to demonstrate to you again why we can use molar ratios in the spot where concentration should go, is because these moles here, if we divide each one to give concentration, we divide by total liters. So that's 85 plus 95. So that would be divided by 180.180 liters. And if we divide these two numbers, this quantity and this quantity, the 0.180 in the denominator is going to cancel out. We can factor that out because it's common with both. So in this case, we can just use moles in our Henderson-Hasselbalch equation. Okay, thanks for watching.